All right, this is the last section that we cover for the semester, and we're going to cover section 6.5 on constrained optimization, Lagrange multipliers, and the extreme value theorem. So our objectives here are to find minimum and maximum values using Lagrange multipliers, solve constrained optimization problems using Lagrange multipliers, and then use the extreme value theorem for two variable functions to find absolute maxes and mins. All right. So, first definition, the method of Lagrange multipliers. So, if you remember before in the last section, we had found maximums and minimums using the D test. Okay, so this is just another way of finding a max or a min using a Lagrange multiplier and when you have constraint equations. Okay, so to find a max or a min value of a function subject to a constraint. So the f of xy is the function you're trying to maximize or minimize. The constraint equation is the g of xy. Basically just tells you how your variables x and y are related to each other. You want to have that one set to 0. All right, so our first step is to form a new function called the Lagrange function. So we'll call it capital F. And it has variables x and y as the original, but we're going to add a third variable, lambda. So this function is established by taking the original function f of xy, subtracting this lambda multiplier by your constraint equation. Okay, so it's the original function f minus lambda times g. So the variable that looks like this, called lambda, is called the Lagrange multiplier. All right, once we've established that function capital F, we find the first partial derivatives with respect to x, y, and lambda. We solve the system of equations by setting those first partials equal to 0. So the ordered triple a, b, lambda is the solution to that system. We're going to determine whether the point a, b yields a max or a min of the function. So as you're solving this, you'll have this extra variable lambda involved. As you're going through your solving process, you may find the value of lambda, you may not. You don't really care. Okay, as long as you get the values of a and b, that's what you need. All right, the method of Lagrange multipliers can be extended to functions of 3 or more. Okay, so if you had a function of a, b, c lambda, right, you could use this same method. Okay, all right, so example 1, find the maximum value of the function a of xy equals x times y, subject to the constraint that x plus y has to equal 20. Okay. All right. So note that this equation is our constraint. So in our definition, we want it set to 0. So it's equivalent to x plus y minus 20 equals 0. So you want to take your constraint equation, set it to 0 first. All right. So the new function f, so this x plus y minus 20, that's your g. Okay. So we'll have our new function, capital F, x, y, lambda, is the original function we're trying to maximize, which was given to be the x times the y, minus lambda times our constraint once it's been solved for 0. All right, so we're going to find our first order partials. Let me go back to that real quick. I kind of went a little bit quick through there. All right, so this is what we're going to find our partial derivatives of. So we're going to find the first partial with respect to x, with respect to y, and with respect to lambda. All right, so partial with respect to x would be y minus lambda. Partial with respect to y, x minus lambda. And the partial with respect to lambda would just be negative x plus y minus 20, because there's no lambdas in those first two terms, or the first term. All right, set each of those derivatives equal to 0 and solve the resulting system. So that's set to 0, this set to 0, and the partial with respect to lambda set to 0. So we have 3 equations, 3 variables. So from the first two, right, you can just solve for x and y and get them both equal to lambda. Substituting x for y in the last equation, since this tells me that x, y, and lambda are all equal. Jump back here real quick. That comes from here. You can say y equals lambda, x equals lambda. So that means that if they both equal lambda, they would have to equal each other, right? That's where they're getting the x equals y equals lambda from. All right, so if we plug that into the last, so take that last equation, if x and y are equal, we can replace x or y with x. We get x to be 10, right? And if x and y are equal, then that means y is also 10, and it means lambda is 10. But remember, we don't really care what lambda is as long as we know what x and y are. So the max value of A, subject to the constraint, occurs at the x and y values of 10, 10. So that would mean that A of 10, 10 is 10 times 10, or 100. Okay, that's it. We don't have to use second partials. We just use first order partials. When you're subject to that constraint, you can find your max and your min. So find the max value of A, subject to a different constraint this time. X plus 2y equals 30. So x plus 2y equals 30 is equivalent to x plus 2y minus 30 equals 0. So your constraint, your g function, becomes x plus 2y minus 30. We form our new function, capital F, as the function we're going to try to maximize, which is the a, xy, minus lambda times our constraint. We find the partial derivatives, the first partial derivatives. So the partial with respect to x would be y minus lambda. Partial with respect to y, x minus 2 lambda. It might be easier here to go ahead and distribute lambda through here before you write these partials down. And then the partial with respect to lambda, there's no lambda here, so that's 0, so it's just the negative of lambda's coefficient. Now we're going to set all those to 0. Each of those set to 0 looks like this. So from the first two equations, we get x equals 2 lambda and y equals lambda. So if y is equal to lambda, that means x is equal to 2y, replacing this lambda with the y. So we're going to come up here to this third equation. So if we got that x was equal to 2y, we can replace 2y with x. So we end up getting x to be 15, right? That's negative 2x plus 30 equals 0. Solves to x equals 15. And remember that x was equal to 2y, so that means that 15 equals 2y, so y would be 7.5. I'm plugging this x right here. All right, so we have the max occurring. The function a is maximized when x is 15 and y is 7.5. So a was x times y, so 15 times 7.5, 112.5. All right, another one. Find the maximum value of f of xy equals 3xy, subject to the constraint 2x plus y equals 8. All right, so we're going to, again, rewrite our constraint as if it were set to 0. So 2x plus y minus 8 equals 0. Form our function, capital F. F of xy lambda is the f of xy function minus lambda times the constraint, g. Find your first partials. Partial with respect to x, 3y minus 2 lambda. The partial with respect to y, 3x minus lambda. And the partial with respect to lambda, negative of 2x plus y minus 8. Set each of those equal to 0, solve the system. Okay, so here we're going to write 3y equals 2 lambda, 3x equals lambda. All right, so we have 3x equals lambda, substituting into the first. They didn't move it over, but you could have. 3y minus 2 times lambda equals 0. So 3y would equal 6x, which means y would equal 2x. So in that third equation, we're going to replace y with 2x. So 2x plus 2x minus 8 equals 0. 4x equals 8, so x would be 2. And if x is 2, plug back into here, that means y is 4. So the max value of f, subject to the constraint, occurs at the x and y values of 2, 4. X is 2, y is 4. And would be the f of 2, 4, so 3 times 2 times 4, or 24. Remember, we use lambda in our system, but we're just using it in order for us to solve for the x and the y. Right? Once you solve for x and y, you could determine the value of lambda. It's just not part of the solution. All right, so if you want to try this one on your own, that might be a good idea to pause the video, try to find the minimum value of this function subject to the constraint. So the g of xy equals x squared plus y squared, and the constraint here is 3x minus y equals 1. All right, so our first step is to set the constraint to 0. 3x minus y minus 1 equals 0. Form your new function, capital G, of xy lambda, the function g of xy minus lambda times the constraint. Find the first partial derivatives with respect to x would be 2x minus 3 lambda. With respect to y, 2y plus lambda. And then with respect to lambda, again, I would probably distribute my negative lambda through here before I wrote these down. It would just be easier to see it. All right, set those to 0. So those were my partials. When we set them to 0, here we would get 2x equals 3 lambda, or 2x over 3 equals lambda. Here we would get lambda equals negative 2y, right? So that would mean that that would equal negative 2y. Thus, 2/3 x equals negative 2y, which means x equals, we multiply this equal to this, multiply by 3/2, you get x equals negative 3y. So plug that into the third equation. Negative of 3 times plugging in negative 3y for x minus y minus 1 equals 0. Clean that up. Gives you y value of negative 1/10. And you could have solved this thing for y and plug that value in for y and solve for x first. It doesn't matter. You're going to plug that back into the equation you substituted to get the x. So you end up with your x value of 3/10 and your y value of negative 1/10. So that minimum is going to occur at that ordered pair, and the minimum value will be what you get if you plug that ordered pair back into the original function g, x squared plus y squared. So 9 over 100 plus 1 over 100, 10 over 100, or 1/10. Whoops, I need to move out of that too quickly. Okay, so general procedure, first of all, set your constraint to 0. Establish your function capital F or G based on the formula. Original function you're trying to maximize or minimize minus lambda times your constraint. Find all your first partials with respect to all 3 variables. Solve that system for at least x and y, and then plug that back in to the original. All right. An application problem. The standard beverage can has a volume of 12 fluid ounces, or 21.66 cubic inches. What dimensions yield the minimum surface area? And then find the minimum surface area. And we're assuming the shape of a can is a right circular cylinder. So let's talk about, before we move on here, why would it be practical to want to minimize surface area of a beverage can? Would have to do with cost, right? If you can minimize the amount of material, which is the surface area, you in turn would minimize the cost, right, of making that container. So if you're producing this and selling it, right, that would be a good business practice. All right, so we want to minimize the function S given by, well, this is the surface area function. So you're just looking up the formula for surface area of a right circular cylinder, which is 2 pi RH plus 2 pi R squared. All right, so that's the formula for surface area in terms of H and R. Subject to the constraint that the volume has to equal, right? This is our constraint, right? It has to be true about our can, that it has to have a volume of 21.66 cubic inches. So setting your constraint to 0 gives you volume, pi r squared h, minus 21.66 equals 0. So this is the formula for volume of the can, right? Volume has to equal that number. All right, so we've established the function we're trying to find the minimum of and established our constraint, right, from reading the problem. So this does require that you know surface area of a can formula and the volume function. All right, so your new function, capital S, would be your function you're trying to maximize, or I'm sorry, minimize right here, minus lambda times the constraint. We're going to find our first partials with respect to h, r, and lambda. So the partial derivative of that with respect to h, 2 pi r minus lambda pi r squared. Partial with respect to r, 2 pi h plus 4 pi r minus 2 lambda pi r h. And the partial with respect to lambda would just be negative of the pi r squared h minus 21.66. Again, I would suggest distributing the lambda, the minus lambda through here and doing your partials after that step. All right, so set each of those equal to 0. So that's those equations for the partials set to 0. All right, so since pi is a constant, let's solve this first equation for r. All right, so here we could factor out pi r, leaving 2 minus lambda r. So that gives me pi r equals 0 or 2 minus lambda r equals 0, which results in r could be 0 or r can be 2 over lambda. Okay, however, r equals 0 doesn't make any sense. If r is 0, it's the radius of the can, then the can does not even exist. So we can eliminate that option. Okay, since r equals 0 cannot be a solution, right, we'll just continue to move on with our problem by using 2 over lambda, right, as our r value. So we're going to plug that into our second equation. So 2 pi h plus 4 pi, plugging in the r, minus 2 lambda pi, again plugging in the r, h. So this was our second partial, or our partial with respect to h, or r, right, with the r value plugged in. We're going to clean that up here. So we get 2 pi h. Here we get 8 pi over lambda minus 4 pi h. The lambdas cancel here, equals 0. So these two terms are like terms. 2 pi h minus 4 pi h. That's negative 2 pi h, right? So if we move it over here, it's positive 2 pi h, right? Equal to 8 pi over lambda, just cleaning it up. So this would mean, if I solve this equation for h, dividing this by 2 pi on both sides, the pi's cancel, we get 4 over lambda equals h. Remember, we had already solved for r. That was this value, right? We're looking for h here. All right, so r equals 2 over lambda, h equals 4 over lambda. That would follow that if you were to solve, say, this one for lambda and plug it in here, right, or vice versa, that h equals 2r. All right, so substituting 2r for h in your third equation, right? 2r is equal to h. We're plugging that into our constraint. Pi r squared times, instead of h, we're plugging in 2r, minus 21.66 equals 0. So the first term becomes 2 pi r cubed. Move the 21.66 to the other side. Divide by 2 pi gives you 10.83 over pi equal to r cubed. And then cube rooting that number is about 1.51 inches for r. Okay, we're going to plug that in here to find our h. So r equals 1.51. That means h is 3.02. That comes from substituting this r value right here, 2 times the r. That's where they're getting the h from. And the surface area is then a minimum and is approximately equal to 2 pi RH plus 2 pi r squared, which comes out to be about 42.98 square inches. So roughly 43 square inches. Sorry. Okay. So I know that one looks a bit messier because the formula involves the lambdas and the pi's, and you just got to pay attention and work through the steps. All right, so that is it. The summary of this section. If an input variable is xy for a function f of xy related by another equation, that's called a constraint. Right? Your constraint just gives you a way the variables relate. Constrained optimization is a method of determining max and mins on a surface represented by z equals f of xy subject to given restrictions or constraints on the input variables. And we use the method of Lagrange multipliers that will allow us to find the max or min of a function subject to the constraint equation g of x, y equals 0. So just a different way of solving a max-min problem when you have constraint equations, as opposed to the d-test that we did in section 6.3. All right, that is it. That is the end of 6.5. That is the end of the material we cover in chapter 6 and the end of the material that we cover for this semester.